Hello, welcome back. In this video, we'll discuss the first part of magnetic field sensors. In this part, we'll give a brief introduction to the magnetic field sensors and we'll discuss the induction coil based magnetic field sensors and the Hall effect based magnetic field sensors. There is a striking difference between the magnetic field sensors and the other sensors. The difference is the magnetic field sensors, they measure the physical quantity indirectly, while in the case of other sensors or the detectors, physical quantity is measured directly. Examples for these type of detectors are light detectors, pressure detectors, temperature sensors, etc. In the case of magnetic field sensors, we have the magnetic field strength sensors, the current sensors, magnetic field direction sensors, etc. Using the magnetic field sensors, one can find out magnetic field strength or the magnetic field intensity. One can measure the current passing through a conductor. One can find out the direction of the magnetic field. The magnetic field sensors, they operate without any contact, meaning there is no physical contact. Since no physical contact is needed, they can be used easily in hazardous conditions and they can be sensed remotely. So remote measurements are possible. The magnetic sensors have been developed utilizing various physical phenomena such as electromagnetic induction, Hall effect, the giant magnetoresistance or the GMR, the tunnel magnetoresistance or TMR, anisotropic magnetoresistance, the AMR, and for applications where highest sensitivity is required, one can also use superconducting quantum interference device. For short, these are known as SQUID. Sensors developed with each of these physical phenomena have their own merits and demerits. For instance, the induction based magnetic field sensor generally will be bulky and they are robust, find applications in industrial sensing systems. They cannot be miniaturized. That is a problem with the induction coil sensors. Similarly, the SQUID sensors, they require superconductors, meaning they need to be operated at low temperatures. To maintain low temperature is a big problem. Even with the advent of high temperature superconducting materials, they involve high cost, complexity, and allow only some of their components to be miniaturized. Whereas the Hall effect, GMR, TMR, and AMR based sensors can be manufactured using planar microfabrication process. Hall effect, GMR, TMR and the AMR sensors, when they are manufactured using the planar microfabrication technique, they become capable of offering high sensitivity with relatively compact footprint or small footprint. Another interesting aspect is their compatibility with CMOS of solid state magnetic sensors with complementary metal oxide semiconductors. The CMOS fabrication processes makes it feasible to achieve integration of sensors with sensing and computing circuitry at the same time. So this makes us what is known as system on chip development, which are highly attractive for Internet of Things, IoT devices. There is a compatibility of solid-state magnetic sensors with the complementary metal oxide semiconductors. CMOS materials are used to process the signal. Because of the compatibility between the solid-state magnetic sensors and the CMOS devices, one can develop the sensor along with the sensing and processing mechanism on the same chip at the same time. Now we shall discuss the induction coil sensors. These sensors are developed based on the electromagnetic induction or the Faraday's law. The induction coil sensors largely used to measure current through a conductor. So if you have a current through this conductor, all around that we'll have an induction coil, and this induction coil will interact with the magnetic field established by the current carrying conductor. Thereby gives us a signal to process, using which one can estimate the current through the conductor. The EMF across the terminals of the coil will be equal to minus N d phi by dt, or which is equal to minus Na dB by dt, where phi is the flux, here A is cross-sectional area of the coil, B is the flux density, and this will be equal to minus mu 0 Na dH upon dt. Here N is the number of turns, mu 0 is permeability, A is area, H is the magnetic field strength. So if the area of the coil is large, then the EMF also will be more. But to achieve a bigger area with the same amount of copper wire, you get less number of turns for the coil. N becomes smaller. So we have to strike a balance between N and A to improve the sensitivity of the sensor. Since the EMF is proportional to the number of turns in the coil, one can go for more number of turns in the coil to achieve a higher degree of sensitivity. However, when the number of turns is increased, we notice that the sensor will become bulky. If N is increased, the EMF V is improved, but this leads to a bulky sensor. To overcome this, one can introduce a material between the conductor and the coil. So one can introduce a ferromagnetic material to improve sensor sensitivity. However, when the ferromagnetic material is introduced, the ferromagnetic material can give rise to certain drawbacks. The first drawback is the properties of the material are not linear. So the nonlinear dependency of the material on temperature, frequency and flux density will affect the measurement. Now we shall see the Hall effect based magnetic field sensors. The Hall effect sensors are transducers measuring magnetic fields based on the principle of Hall effect. So these are transducers measuring magnetic field strength based on the Hall effect. The Hall effect is a result of magnetic Lorentz force. If a solid, when placed in an external magnetic field B, the magnetic Lorentz force acting on the charge carriers is given by F is equal to QV cross B, where Q is the charge of the charge carriers, V is the instantaneous drift velocity of the moving charges, B is the flux density in which the sample is placed. The instantaneous drift velocity can be obtained using V is equal to I over NQWD, where W is the width, D is the thickness, I is the current. When the magnetic field is applied perpendicular to the direction of the current flow, then the magnetic Lorentz force causes a deflection of the current. As a consequence, charges of opposite sign accumulate at two surfaces orthogonal to the current flow. Suppose this is the specimen placed in a magnetic field. And if you have a current in the specimen, the charges will be deposited on the outer edges of the specimen along the width of the specimen, meaning opposite charges are deposited on the opposite sides of the specimen. In this case, we see negative charges are deposited on this side and positive charges are deposited on this side, and that is essentially the Hall effect. So magnetic force on negative charges will be on this side, the electric force from charge accumulation will be on this side, and you have the magnetic field pointing upward. So one can write QV cross B as VHQ upon W. VH is the potential difference observed between these two surfaces. So VH can be written as IB upon NQD. This can be rewritten as B is equal to VH NQD upon I. In this expression, VH can be measured. N is the number of charge carriers that can be obtained. Q is the charge on the charge carrier. D is the thickness of the specimen. I is the current. So thereby one can estimate the flux in which the specimen is placed. Here VH can be positive or negative depending on whether we are using a semiconductor of N type or a P type. One can measure the magnetic field intensity. So the Hall effect sensors, they possess a large number of advantages. The first one is they are easy to manufacture and they can be scaled down. Integration with the CMOS circuits, and the response is linear. It is highly repeatable. Robustness can also be achieved in Hall effect based magnetic field sensors. In this video, we gave a brief introduction to the magnetic field sensors. We have also discussed the induction coil based magnetic field sensors and the Hall effect based magnetic field sensors. We have said that physical quantity is measured indirectly in the case of magnetic field sensors, whereas in the conventional sensors, the physical quantity is measured directly. The conventional sensors such as light sensors, pressure sensors, temperature sensors, they measure the physical quantity directly. The magnetic field sensors, they measure the current, they can also measure the direction of the magnetic field intensity, etc. A striking difference exists between magnetic field sensors and other sensors. That is, no need to have physical contact. Remote measurements are possible in magnetic field sensors. The magnetic field sensors are developed using various physical phenomena. The physical phenomena used to develop the magnetic field sensors are electromagnetic induction, Hall effect, giant magnetoresistance, tunnel magnetoresistance, and the anisotropic magnetoresistance or the AMR. The places where high sensitivity of measurement is required, one can adopt the SQUID, the superconducting quantum interference device. We have seen the induction coil sensors. We have said that they are bulky and they cannot be miniaturized. SQUID sensors have their own problem. The problem is they use superconductors. As a result, they need to be always maintained at low temperatures. So the Hall effect, GMR, TMR and AMR based solid state sensors can be fabricated using planar microfabrication process. So as a consequence, their sensitivity is relatively high and footprint is relatively small. Compatibility of solid-state magnetic sensors with complementary metal oxide semiconductors (CMOS) fabrication processes makes it feasible to achieve integration of sensors with sensing and computing circuitry. The compatibility enables the manufacturing of system-on-chip based circuitry. Can have a very large number of applications in Internet of Things. We have seen the induction coil sensors. We have said that electromagnetic induction or the Faraday's law is used in the induction coil sensors. So from the Faraday's law, one can write the EMF is equal to minus N d phi by dt, where phi is flux, N is the number of turns in the coil. This can be written as minus mu 0 N A dH by dt, where N is the number of turns, A is the area, H is the magnetic field strength. The magnetic field strength is produced by the current carrying conductor that is passing along the axis of the coil. By introducing a ferromagnetic material, one can improve the sensor's sensitivity After that, we have seen the Hall effect based magnetic field sensors. It is based on the magnetic Lorentz force. A specimen carrying current, when placed in a magnetic field, the charge carriers in the conductor will experience Lorentz force, and the magnetic Lorentz force acting on the charge carriers is given by F is equal to Q V cross B. So one can measure the potential difference that is established as a result of the magnetic field. Thank you.